Hi, welcome to today's math lesson on representing linear proportional situations with tables and equations. Starting with our do now, we have the diagonal lengths of three rectangles are shown. The rectangles are not drawn to scale. Rectangle P is 6.7 centimeters. Rectangle S is 34/5 centimeters. And rectangle T is square root of 36.5 centimeters. The question is, which list shows the rectangles in order by their diagonal lengths from shortest to longest? So from smallest to largest, from least to greatest. So the first thing that I'm going to do is transform 34/5 into a decimal, or translate it into a decimal. So all I do is divide 34 by 5 and I get 6.8 centimeters. Then on a calculator, I figure out what the square root of 36.5 is, and that's about 6.04 centimeters. And so now that I have all of the lengths of the diagonals in decimal form, I can figure out what's the smallest decimal. So the smallest is going to be rectangle T. And then the second smallest is rectangle P. And the longest is going to be rectangle S. So that was answer choice B, with rectangle T, rectangle P, and rectangle S. Today's TEK is 8.5a. Our lesson target is scholars will represent linear proportional situations with tables and equations in the form of y equals kx. Our DOL is given 4 problems. Scholars will represent linear proportional situations with tables and equations with 100% accuracy. Some review of academic vocabulary are the words constant and consonant proportionality, which can be used interchangeably, which means that both are referring to the same thing. Equivalent ratios are like two fractions that are equal to each other. So in this first example right here, where we have a table and the word proportional on top, we can figure out that a table's relationship is proportional by making a proportion with the x and the y coordinates. So in this case, we have x on top, y on bottom. So we have 2 comma 6 becomes 2 over 6, and then we have 6 comma 18 becomes 6 over 18. And if we reduce 2 over 6, we get 1/3. And if we reduce or simplify 6 over 18, we also get 1/3. So that's how we know that the ratios are equivalent, making the table proportional. For non-proportional tables, if we try to do the same thing, so we have our x value on top, our y value on bottom, and then we simplify or reduce those fractions. So we have 2 comma 10 becomes 2 over 10, and then 6 comma 22 becomes 6 over 22. If we simplify 2/10, we get 1/5, and if we simplify 6 over 22, we get 3/11. So the ratios are not equivalent, and that's why this table represents a non-proportional relationship. Ordered pairs is another word for a coordinate or a point. So it's always in the form x comma y. So your x coordinate's always first, and then your y coordinate's always second. The origin is a specific point. It's at 0 comma 0. And we'll go into the next few vocabulary words in the next slide. So just a quick overview of proportions. Proportions consist of ratios, and ratios can be written in 3 different ways. They can be written with a colon in between 2 numbers, or with the word to, spelled T-O. The way that we've been using ratios in our lessons is as a fraction. So 2 to 6 would be 2 over 6. And then proportions are equivalent ratios. So 5/10 is equal to 25 over 50 is equal to 35 over 70. And unit rates are ratios with a denominator of 1. So for example, we have 12 inches over 1 foot. So our bottom number, our denominator, is 1. And then for $1.25 per pound, if we wrote that as a fraction, it'd be 1.25, or 1 and 25 hundredths over 1. Welcome to today's math lesson. Our TEK is 8.5a. Our lesson target is that scholars will represent linear proportional situations with tables and equations in the form of y is equal to k times x. And our DOL is given 4 problems. Scholars will represent linear proportional situations with tables and equations with 100% accuracy. Some vocabulary words that we need to know for this lesson are the words constant and constant of proportionality, which are the same thing. Equivalent ratios. So in this example picture right here, we have a table and we have a proportion. So that's 2 equivalent ratios. So we have the x value on top and then the y value on bottom. So 2 comma 6 actually becomes 2 over 6, and 6 comma 18 becomes 6 over 18. And if we reduce or simplify both fractions, we get 1/3. So that's how we know that the ratios are equivalent, and that's what makes this table a proportional relationship. For this example on the right, doing the same thing, we have our x coordinate on top, our y coordinate on bottom. We have 2 comma 10 becomes 2 over 10, and 6 comma 22 becomes 6 over 22. If we reduce 2 over 10, that becomes 1/5. And if we reduce 6 over 22, that becomes 3/11. The ratios are not equivalent, and that's what makes this a non-proportional relationship. Ordered pairs is another way to call a point or a coordinate. So it's always in the form x comma y. Your x coordinate comes first, and then your y coordinate always comes second. The origin is a very specific ordered pair or point. It's 0 comma 0. And we'll go over the words ratio and unit rates in our next slide. So as a review of proportions, proportions are made up of ratios that can be written in 3 different ways. So one way is using a colon to separate the 2 numbers, so 2 to 6. And then another way is using the word 2 spelled T-O, so 3 to 4. And the last way is as a fraction. So if we were to rewrite this 2 to 6, as a fraction, it would be 2 over 6, but we would still read it as like 2 to 6. Equivalent ratios, so 5/10 is equal to 25 over 30, which is equal to 35 over 70. And so proportions are equivalent ratios. And unit rates. Unit rates are a type of ratio with the denominator of 1. So we have 12 inches over 1 foot. And then our second example is $1.25 per ounce, which if we wrote as a fraction would be 1.25 or 1 and 25 hundredths over 1. This first I do problem reads 15 bicycles are produced each hour at the Speedy Bike Works. Show that the relationship between the number of bikes produced and the number of hours is a proportional relationship. Then write an equation for the relationship. So this first statement was already put into the table. So our hours is going to represent our x units or our x values, and our bikes produced is our dependent variable, and that's going to represent the number of bikes produced. So in 1 hour, 15 bikes were produced. The first thing that I'm going to do is find out what my constant of proportionality is by using this equation. K is equal to y over x. So our y value is 15, our x value is 1. So 15 over 1, or 15 divided by 1, is 15. From there, I'm going to write an equation, which is always in the form of y is equal to k times x for proportional relationships. So since my constant is 15, my equation is going to be y is equal to 15x. And now I can fill in the y values by plugging in the x values into the equation. So 15 times 0 is 0. 15 times 2 is 30. And 15 times 4 is 60. And to answer this question, how can we verify? Verify means confirm or be sure of that this is a proportional relationship. What I'm going to do is if I divide or find my constant of proportionality for each of the pairs of points, it should all be the same, and it should all be 15. So if I do 60 divided by 4, that's 15. 30 divided by 2, that's 15. And 15 divided by 1, that's 15. The only exception is 0, 0, because 0 divided by 0 is 0, but that's what makes it a proportional relationship, because it has a point at the origin. This I do question reads, the equation y is equal to 10 times x, where x is the time in minutes and y is the distance in inches, shows the relationship between the distance that a snail crawls and the time that it crawls. And we have to complete the table below. So we are given our equation, and time is going to be our x variable, or our independent variable. Usually time is our independent variable, and that makes y our dependent variable, which is represented by distance in inches in this case. So I can plug in any x value. So I'm just going to say 0, 2, 5, 7, 10. And then from here, I'm going to plug in these x values into the equation. So 10 times 0 is 0. When x is 2, 10 times 2 is 20. When x is 5, 10 times 5 is 50. When x is 7, 10 times 7 is 70. When x is 10, 10 times 10 is 100. And we can verify, or we know that this relationship is proportional, because if we divide our y by our x, or we basically find our constant of proportionality for each pair of points, 100 divided by 10 is 10, 70 divided by 7 is 10, 50 divided by 5 is 10, and 20 divided by 2 is 10. This we do problem reads, write an equation that describes the proportional relationship between the number of days and the number of weeks in a given length of time. So time in weeks and time in days. Time in weeks is going to be our x variable, or independent variable. In a table that's flat or horizontal, the top row is always going to represent the x values, and the bottom row is always going to represent the y values, or the y variable. So from here, we have to first figure out our constant of proportionality. So we have k is equal to y over x. And the only complete column in the table is this 1 and 7. So we have 7 is our y value, and 1 is our x value. So 7 divided by 1 is 7. And from here, we can write our equation, which is always in the form of y is equal to k times x. So we have y is equal to 7x. And now we can plug in our x values into the equation to figure out what our y values are. So when x is 0, I'm multiplying 7 times 0, and that's 0. When x is 2, I'm multiplying 7 times 2, and that's 14. When x is 4, I'm multiplying 7 times 4, and that's 28. When x is 10, I'm multiplying 7 times 10, and that's 70. So for this column right here, we're given that y is equal to 56, and we're trying to find our x. So when we know our x value and we're trying to solve for our y, we multiply. But if we know our y value and we're trying to solve for our x, we're going to have to do the opposite, which is dividing. So what I'm going to do is I'm going to plug in this 56 into this equation that we came up with. So we have 56 is equal to 7 times x. So 7 times x, we want to move this 7 to the other side, so we just have the x alone. That's called isolating the variable. So to isolate the x, we're going to have to divide both sides by 7, because we're doing the opposite operation, also called the inverse operation. 7 divided by 7 is 1. So then we're just left with x, and 56 divided by 7 is 8. So that was our x value when our y value is 56. Then we have another question. It says, how many weeks are in 119 days? So our first step is to figure out this 119. Is that our x or our y value? So if we look back at the table, time in weeks is our x value and time in days is our y value. So this is our y value. Then I have to think, I have my y and I'm trying to find my x. So am I multiplying or dividing? Well, Since we just solved for our x given our y value, we divided, I know that we're also going to have to divide again. So we have, instead of y is equal to 7x, I'm going to write 119 is equal to 7x. And again, we have to isolate the variable. So to do that, we're going to have to divide both sides by 7. 7 divided by 7 is 1. So we have x is equal to 17. And x is representative of the time in weeks. So our unit should actually be 17 weeks. There are some you-do problems. And lastly, your DOL, which is in a Google form and it's 4 questions. Thank you so much for following along in today's math lesson, and see you in the next math video.